Good afternoon. So thanks for coming. It's a great honor and pleasure to host Andy Millis today. Andy, he got his PhD at MIT, and then he was on technical staff of AT&T Bell Labs. And then he was on faculty in Rutgers University, Maryland, and then at Columbia University, starting from early 2000s. And he's there ever since. Andy is a virtuoso of both analytical and numerical methods of condensed matter theory. He is a Paganini of methods. But what sets Andy apart is that he is keenly interested and deeply understands properties of materials. And this combination at this level is very rare to come by. And over years, it produced amazing results, amazing works that helped us understand better the most intriguing properties of strongly correlated electron materials, such as high-temperature superconductors. Some people in the audience actually know not the most famous papers, maybe, but still very useful. It's what MMP or PMM paper, Millis, Monian, and Pines, right, on relaxation of nuclear spins in high TC. And this is kind of a small part of what Andy was doing for high TC. And then colossal magnetic resistance is another great subject. And in general, properties of conductors where itinerant electrons conspire to be almost magnetic, and it's a great part of a very interesting, more general theme of quantum magnets. And lately, Andy did an impact in low-dimensional electron systems and systems far away from equilibrium that one can get by exciting condensed matter by short pulses of light. Strong and short pulses of light. On top of that, Andy played and plays an amazing role in just organizing physics community. He did a lot for Aspen Center for Physics, for Kavli Institute of Theoretical Physics in Santa Barbara, for Cavendish Lab in UK. He did amazing things in Columbia University, and condensed matter group, experimental and theory group, is amazingly interesting, at the forefront, cohesive and diverse. And lately, Andy also spearheaded the math and physics programs in Science Foundation, in Simons Foundation, and now he's co-directing the Institute of Computational Quantum Physics. Which kind of burst into scene not long ago, and already have amazing physics done. And we are happy today to hear a small part of this story that is driven in no small part by Andy's vision and Andy's talent as a physicist. So with that, welcome. Looking forward to your talk.
Wow. Well, thank you. Thank you very much. With that very overly generous introduction, I should quit while I'm ahead. So, I will say briefly just that, in particular, the Flatiron Institute, with which it has been my privilege to be associated for a while now, is a testament to what you can do with inspired leadership from Jim Simons and a reasonable amount of finance. And all we really had to do, given that, was hire some outstanding people, which we were fortunate enough to be able to do. And in fact, what I want to talk to you about today is work which is done in part with, let me see, is this going to make the pointer point? Oh, is it turned on? That's better. That's the two important questions of experimental physics. Is it plugged in and is it turned on? So anyway, this work is done in part with a product of Yale, Alex Georgescu, who came to us who came to the Flatiron Institution after doing his PhD with Sorab here. and with whom I've been fortunate to collaborate both while he was a postdoc and subsequently, up to now where he's landed as a faculty member in chemistry at Indiana. And Denis Golesh, who was a postdoc at Flatiron and is now back in Ljubljana, and Jiwan Sun, who was from the Columbia side of my life and is now at Tsinghua University. The work is supported by various government agencies via block grants, the Columbia EFRC Energy Frontier Research Center from the Department of Energy, and the Materials Research Science and Engineering Center from the NSF and the Flatiron Institute. So what I want to do is talk about order parameters in strongly correlated electron systems and their uses both in and out of equilibrium. Okay, so specifically in the equilibrium context, I'm going to talk about how one might construct a free energy landscape for some of the systems that we're interested in. And then for beyond equilibrium, I'm going to give you something which is really perhaps closer to poetry than science about how we use these energy landscapes to interpret some of the experiments. And I should also say, please stop me at any point and ask questions. Okay, so let me start with some motivation. All right, here's a material, calcium ruthenate. It's a cousin of a material some of you may have heard about, strontium-2 ruthenium-04, which is an exotic superconductor and interesting, strongly correlated Fermi liquid. Anyway, this material has a high temperature metal to low temperature insulator transition. You can see here an electrical resistance versus temperature. High temperature, more or less weakly temperature independent, relatively small resistance, low temperature, rapidly rising resistance, a transition in between. And this is associated with a noticeable change in the crystal structure. Okay, in particular, the basic unit of this material is a ruthenium oxygen octahedron, shown here. And when you go through the transition, the octahedron flattens. So that's a structural change. For those of you who like these things, it's symmetry preserving, same structure on both sides, but just different atomic positions. And associated with that, there is a change in the occupancy of some of the ruthenium orbitals. You go in the high temperature phase from a case where the 3 relevant ruthenium orbitals are equally occupied to in the low temperature phase, 1 orbital is doubly occupied and 2 are singly occupied. So there's a mixed electronic and lattice transition. Okay, now this transition is remarkably sensitive to all kinds of perturbations. In particular, in very interesting work that Harry Nair, who was a student of Darrell Schlom and has now moved on, did, and for reasons I totally fail to understand, never published. They showed that the transition was extremely sensitively dependent on what substrate you grew the material on. And growing the material on different substrates, basically, if you like, applies a strain. For one substrate, the atomic distances in the plane are a little bigger than in the equilibrium structure. For another substrate, they're a little smaller. And you see that depending on which substrate, you can either make the transition completely go away by keeping it always metallic, or keeping it always insulating, or just move it around a little bit in temperature. Okay. Now, this is one example of an old subject which has had controversy for probably as long as I've been alive. One example is vanadium dioxide. Here is the more or less discovery paper from a long time ago. You see this is a material which again has metal and insulator phases, which you can tune between by changing temperature and by changing pressure. Associated with the transition, there's a change in the lattice structure shown here, just as the ratio of the in-plane to the out-of-plane lattice constant. Here's another example, vanadium dioxide, which I'm told is actually used in commercial bolometers. It has a very sharp metal to insulator transition at a temperature a little bit above room temperature. And apparently, it's commercially viable to put the temperature, average temperature right here. And the resistance versus temperature is so steep that a tiny amount of absorbed infrared radiation changes the temperature enough to make a measurable change in the resistivity. Right? So it's night vision, basically. All right. Again, in this thing, it's kind of hard to see from these pictures, but there's an obvious change of electronic state and it's associated with a change in crystal structure. The red things here are the vanadium atoms. And although it's hard to see from this, basically, the vanadiums come in pairs, and the length of the vanadium-vanadium dimer gets a lot shorter in the insulating phase. Yet another example, the Republican in name only compound. R stands for one of the different rare earth or actinide series. This material, depending on what material you put, has a metal insulator transition at some temperature. For a wide range of parameters, there's a metal insulator transition is at a much higher temperature than the magnetic transition. The metal insulator transition is first order. It's associated with a large change in resistance, and it's associated with a change in the mean nickel-oxygen bond length. The basic unit is, again, a nickel-oxygen octahedron. And when you go from the high temperature metallic phase to the low temperature insulating phase, what happens is you get a two sublattice distortion, where the one nickel-oxygen set of bonds becomes shorter by some amount, the other one becomes longer, the average length doesn't change. You see that for a couple of the materials up here. These are measurements of just the long and short bonds. And this is associated in a complicated way I don't want to get into here with a change in the charge density on the nickel sites. So again, there's an electronic and a structural transition. And again, you can play games. Some of these experiments were done here at Yale, some in Geneva. You can put it on substrates and things like that, and for sort of the same reason, move the transition around substantially. Okay, so to summarize, there's this whole family of metal insulator transitions in which there's some kind of electronic order parameter, a little bit different for the different cases, coupled to a lattice degree of freedom, typically linearly. This coupled system has a transition between two quite different states, which has sometimes useful properties. This transition can be strongly controlled by pressure, strain, chemical composition, and so on. And there's been 50 years plus of arguments about whether the transition is driven by lattice energetics, so just the atoms decide they want to move and the electronic state follows, or by electronic physics. The electrons want to change their state into some insulating state, and the lattice follows. All right? And the answer to this question has a lot to do with how you want to think about controlling properties of these materials. Okay, now, another dimension which has surfaced recently, you may also drive these materials out of equilibrium. Here is one of many examples. I'm choosing it. It's this beautiful work done by Anita Verma and her PhD supervisor, Andre Singer at Cornell, and Dennis and I were a little bit involved. It's going to appear here. Anyway, so you take this calcium ruthenate material, which I showed you before, in its lower temperature insulating state, and you irradiate it with a pulse of some amount at an energy which is high enough to excite carriers out of the ground state into the next excited state. Okay, now it's not shown here. I'll come to this on the next slide, but if you excite it weakly, nothing much happens. If you excite it above a certain threshold, then three things happen. Well, first, this red curve, which happened, this is a plot of things versus time. And this red curve just shows that the excitation that you made does something, essentially immediately. This is the reflectivity at essentially the band edge. The black thing is a change, which I'll come back to in the lattice structure. And the purple thing, which is rather slower, is a change in the low frequency electronic structure, which is a reasonable proxy for is it metallic or not. This is one of these cases where you can't actually put wires on this non-equilibrium thing and measure its electrical resistance. So you have to use proxies like the low frequency reflectivity. Okay, now here's what happens to the lattice. They look actually at a particular X-ray scattering peak. In fact, the 008 peak, which is connected with the C-axis lattice parameter. All right, so what you see is that before irradiation, this peak is here. After irradiation, the peak moves down in reciprocal space, meaning that the lattice parameter is getting longer, right? And it goes back, in fact, to the lattice parameter you would expect in the high temperature metallic state, right? And remarkably, it just stays there for a very long time. And remarkable number two is that the electronic properties follow the lattice only after a noticeable lag.
So which time it gets back to
Longer than this. They don't know. Basically, for technical experimental reasons, which I'm not fully on top of, basically they can't go to more than 100 picoseconds. It does get back to it on the time of probably nanoseconds, but they don't know at what time. Yeah. Yeah, it doesn't stay forever in the non-equilibrium state, but it stays for a remarkably long time. Yeah.
You know what you mean by the lag?
Oh, yeah. All what I mean is here, look at the black thing. That's this measure of where this peak position is. And now the purple thing is the terahertz reflectivity. And you see this one turns on rather slower than that one.
The terahertz is about a picosecond.
Yeah.
Is there?
Yeah. So this is a bit longer than that. Okay. This is what I said before. Basically, if you hit it very lightly, nothing much happens, except for an increase in scattering intensity, which I'll tell you about more later. You hit it hard, and the peak position shifts. Okay, now, here's the final part. And this is slightly sketchy, and it will take a minute to explain, but bear with me. The knock on all of these non-equilibrium experiments is you hit the system hard, so you're dumping a bunch of energy into the system. So the first thing you might think is, well, you're just heating the sample. And this is simply a very expensive and inefficient way to heat the sample back up to the temperature where it would be metallic anyway. All right, so here's the argument that it's not. This is a slightly complicated plot, but the basic statement is that in particular for this 008 peak, there's an almost perfect not complete because you can see the peak, but a almost perfect destructive interference, right? So the amplitude of this peak is intrinsically low compared to other peaks. However, if you heat the system up, then you get a lot of thermal fluctuations. You get a Debye-Waller factor that messes up the destructive interference. So the peak amplitude goes up. All right. So this thing is a plot of the change in peak position, interpreted as a change in c-axis lattice parameter, versus the change in peak intensity. All right. The green thing is equilibrium. You go through the transition, which is really about here, and you see that an increase in the lattice distortion is associated with a large increase in the peak intensity, therefore a large increase in the Debye-Waller factor. You do the strongly non-equilibrium probe, you see a similar increase in the lattice parameter, but much less increase in the peak intensity. So this is the argument that it's not just heating. You haven't put it into a state which is like the high temperature state with the same lattice constant, because you have much less destructive interference than you would in the high temperature state. All right. So it's not a proof, but it's suggestive, I would argue, and that's the best I think that can be done in this class of experiments. So let's just assume, based on this, that we go to a non-thermal phase, which can live for a long time.
So
Yeah.
Not the same as heat, so what you're saying.
Correct.
I guess my quick question is about domains.
Yeah.
How does the width of the Bragg peak change?
So statement question one was this is not about heating, which is yes, and then question two, just for the people, whoever may be watching this on Zoom, is how does the width change? Not a lot. Although to be fair, I'm not sure how good a metric that is, because this is a film grown on top of a substrate, and there's probably an intrinsic width in there, which is limiting the resolution of changes in the width. Okay, so this is just to summarize what I said. You have a low fluence, things just relax back to their equilibrium state. A high fluence, you get a long life change. The long time state is apparently non-thermal in the sense I gave, and the electronic properties change more slowly than the lattice. Okay, here's another example, which I'll come back to. This is a particular material in the high transition temperature cuprate class of superconductors. It's a peculiar one because it has a superconducting phase with a transition temperature that depends on carrier concentration. And the superconducting transition temperature has a pronounced minimum at a carrier concentration of 1/8 carrier per unit cell. This carrier concentration is associated with a charge and spin order, with a competing order, basically. All right. So again, our ultra-fast friends, in this case, Rick Everett at San Diego, did experiments where you take a sample somewhere around here and you irradiate it. And what you find, is that after you irradiate it, it looks more superconducting than it did before, right? So these are equilibrium and non-equilibrium measures of more or less the electromagnetic response, and the difference between gray here and red/blue is the difference basically between a superconducting and a non-superconducting thing, right? So the interpretation is that the irradiation has destroyed the competing order, allowing the superconductivity to grow up in its place. Okay, and this is the paper where, yeah.
Activity is superconductor, I guess.
Mm-hmm.
Which goes.
Yes. But in fact, what they've done in various ways that I don't want to go into here, you should look at the paper, is analyze. But here's just the basic reflectivity. This is two things from before. And here is red and blue superimposed after. So you see the reflectivity is higher. They've converted the reflectivity into conductivity, and you see that basically what you get, especially for the dissipative or reactive part of the conductivity, is this large negative thing, which is characteristic of superconductivity. Yeah, exactly. So that's the reactive response that tells you that you have superfluid carriers. Okay. All right. So now one would like to think about these experiments, right? And the problem is that they're not at all amenable to direct computation. Basically, what you want to do in each of these cases is solve the Schrodinger equation starting from an initial condition and see what happens. And what we can get to, as I'll show you a little later with some rather brutal approximations, is few to tens of femtosecond timescales, which is factors of 10 to 100 less than the timescales we're really talking about, right? So you need some way to connect the short times, which are computationally accessible, to the long times that you're interested in. Okay. All right, so this is what I said. So now to start the theoretical part of this talk and tell you how I would like you to think about this, let me go back to something extremely simple, right? Which is a material that has a second order phase transition. All right, and let me suppose that there's a second order phase transition and there are two things, two order parameters, let's say an electronic order parameter, which I'll call eta, and a lattice order parameter, which I'll call q. All right, so if I just write down a Landau theory to quadratic order, I have some terms: a stiffness against changing the lattice, a stiffness against changing the electrons, and a cross coupling. All right, and let's imagine the undistorted state has all these things equal to 0. So I will get a transition. Well, this thing will be stable if the eigenvalues of this quadratic form are all positive, and I'll get a transition if one of them becomes negative. Okay, so then once you see this, you can make an obvious taxonomy. All right, I will say that this is an electronically driven transition if this guy changes sign, and then the cross coupling will just move my transition temperature around a little bit. I will say I have a lattice-driven transition if this guy changes sign, and again, the cross-coupling will move things around a little bit. And I will have a mixed transition if neither one of them changes sign, but because the cross-coupling is strong enough that the lowest eigenvalue can change sign, right? So that's an elementary taxonomy of electronic, lattice, or mixed transition. Okay. So this was implemented in a really beautiful paper by Ian Fisher. The citation will be on the next slide. Ian settled a controversy related to some of the iron arsenide superconductors, which exhibit a phase transition from a high temperature state where the crystalline symmetry is square to a low temperature state where the crystalline symmetry is rectangular. So you break C4 down to C2, right? And there was controversy for a number of years about whether this transition was driven by electronic or lattice effects. All right. So what Ian and his collaborators did, this is the paper, was find a clever way of measuring electronic properties at a fixed value of the lattice coordinates. All right. What they did was, in fact, they fixed strain, or they varied strain over a small range, and they measured the anisotropy and the electrical resistance. Right? So if you have a C4 symmetry, there's no anisotropy. If you put on some strain in a particular direction, it breaks the symmetry down to C2, you get some anisotropy, and you can ask how big of a change in the anisotropy of the resistance do you get? All right. So that is a proxy for this coefficient, right? Because what you're saying is you fix the lattice, then you solve for this thing. Your solution, right, gives you a value. I wrote the inverse here, which depends on the coupling here and how strong you change the lattice, right? So this is a plot of their results, and what you're supposed to see is that the inverse of the resistivity anisotropy, that is the inverse of our electronic order parameter, has an approximately linear temperature dependence, and then in what I think is a spectacularly bad piece of public relations, they don't extend the plot down to 0, but you can easily see that this would cross 0 about here at 70 Kelvin. So this is a statement that in this material, the transition is intrinsically electronic, just boosted up from the, say, 75 Kelvin that you would get by extrapolating this line to 95 Kelvin by the cross-coupling, right? So this was a very important paper because it showed there was an intrinsically electronic nematic, that is to say C4 to C2 transition in a material. Okay, now what Alex and I did was essentially to take this set of ideas and apply it to the first order transitions in correlated electron materials. Yeah.
But the blue points there, so explanation is great, but why is the blue points are not fully extrapolation?
Think of a ferromagnet in a magnetic field. That's all this is. No. Then once you're in the ordered state, it's different, right? Because then you have an order parameter, which is going to keep it doing something else. So then what you're seeing is changes around an ordered state.
Right.
So that's why only look at the temperatures above the transition temperature. Once you're in the ordered state, the analysis has to be different, right? I've given you an analysis which is only in the disordered state.
You know that if there's some conditions, then that would be some kind of a kink in some derivative.
Well, but more or less, you're seeing this. Yeah. It's not a precisely sharp transition. I mean, there's a lot more to say about this. But the basic fact is that they could tease out an electronic property at fixed lattice and just from its temperature dependence over a reasonably wide range, make it very natural to believe that there was an intrinsically electronic transition. Yeah, but basically, if you go back to what you know about a ferromagnet in a magnetic field, you will see this. Okay, all right. So this is the work with Alex. All right, and the problem we have, if you want to address this theoretically, is that the current, let's say, many-body methods for materials are very good at delivering to us an electronic configuration for a given set of atomic positions. All right, so in other words, they're very good at, well, very good. They're good at giving us an equation of state. Right, you fix the atomic positions. There's some kind of free energy, which the calculation is in effect minimizing at fixed value of the lattice to give you an electronic configuration. All right. So the question is, knowing this equation of state, electronic configuration as a function of lattice, how do we extract the free energy, the full free energy function from the solution? Okay, and I've glossed over a lot of things here. I mean, just I said our many-body methods deliver this. That was a major part of Alex's work and a fair amount of work, quite a lot of work before that in CCQ and other places. But let's just assume that you have some method for doing that. Okay, now The reason why you can make progress is that in most of the correlated materials we care about, there is a separation of bands. This is a band structure for this calcium ruthenate material. The red things are the electronically active ones that you care about. Apart from a little bit of overlap, they're well separated from a large number of other bands. And they contain a very small fraction of the electrons in the material, right? So what that means is that you can partition the energy or the free energy into one thing which depends on the lattice configuration and the electronic configuration, and everything else which just depends on where the lattice is, right? And this thing gives us the dominant contribution to the lattice energetics. All right. The second thing, and again, I'll be happy to discuss this offline, is that we know a priori how this depends on, or at least we have a reasonably good guess on how the coupling term depends on the lattice coordinate. In particular, the electronic coordinate is linearly coupled to the lattice coordinate, and we have reasonable ways of estimating that coupling. All right. So what that tells you is that our free energy really looks like this. We have a lattice part, which we can get from elementary methods. We have a cross-coupling, which we can get. And this is where all the fancy physics is hidden. So that means that I can write down the equation of state immediately. And to get the full free energy, basically, I just have to integrate this thing back. What we actually do is fit the solutions to an appropriate symmetry-guided polynomial and then just write down the integration. All right, so I'm going to give you two applications of this. These are these two materials which have different symmetries, different electronic orders, etc. All right, so here's our rare earth nickel oxide thing again. In this case, the lattice mode is really just the bond disproportionation, which is almost exactly an eigenmode of the lattice. And the electronic order parameter is the charge in a suitable Wannier basis on the two nickels. All right. So here is our calculated results for the equation of state, that is the electronic order parameter as a function of lattice distortion for different materials. You see a first order structure, right? And then you see a line, which is just the lattice contribution to this energetic. So your allowed solutions are the intersection of the heavy red curve and this other thing. And then the green things are our fits to a sixth order polynomial.
You can define, somebody defines the order parameter or something. You're saying, although the parameter delta n.
Yeah, yeah, right. Which is again defined precisely as the occupancy of some Wannier orbital. We can talk about that later. Okay. So then you can integrate it back and you get this very interesting energy landscape, which looks sort of like diagrams you see in string theory, where you have a minimum at 0 lattice distortion and 0 electronic distortion, which is locally stable. You have another minimum, well, 2, because they're related by symmetry, you have to choose which sublattice gets, which involve both an electronic and a lattice distortion, and nothing else in between. This minimum is locally stable. There is no minimum with lattice only and no electronic distortion. There is no minimum with electronic distortion and no lattice distortion, right? So in this compound, the electronic and lattice degrees of freedom are inextricably coupled, and the transition is driven neither by one nor the other. All right. Now it's interesting to look at this in a little more detail. Yes?
You said sometimes you want to know what started, which was the underlying cause.
Yeah.
What's the operational way to tell when something happens?
Well, here, to me, the first answer is this. All right, I'll come back to the non-equilibrium one a bit later. But just in terms of equilibrium free energy, the statement is that you need both distortions working together to stabilize the ordered state. And that there is just nothing if you look only at one or only at the other. There's not even a metastable minimum. Okay.
So maybe the other way to put the question. So it's a taxonomy, but it's not canon, right? So basically it's something small. And the question is that this again, I think delta n is at most 1. What about Q? Is it all sport?
Things, I don't have a good answer to that because the problem is after you go beyond about 0.15 in these units, or maybe 0.2, the lattice energy gets very strongly nonlinear and all kinds of weird things happen to the chemistry. So the way I would say it is that delta Q can't be much bigger than about 0.15 or 0.2, otherwise the whole scheme breaks down and you have to start over, basically.
So when you're saying that it's mixed, this 0.05 is about half of what in principle is possible with Q.
Or a third, something like that, yeah. Yeah. Right.
Okay.
But to me, the mix really, just to repeat myself, there is not even a metastable minimum if I set delta n equals 0 and scan in Q. There is not even a metastable minimum if I set Q equals 0 and scan in delta n. That's what it really means to me. Right. But now let's deconstruct this a little bit. Okay. So here I'm showing you the electronic part and then the full free energy minimized as a function of electronic part minimized with respect to the lattice coordinate, or minimized with respect to the electronic part as a function of the lattice coordinate. So just look at these. The three colors are three materials. The red one, you can't even see, its transition temperature is up here. The blue one is this one. The red one, the green one is this one. Okay, and what you see, and the one I showed you before is just a little bit on the side of the green one. Neodymium is there, right? So what you see is that the purely electronic energy actually only for the most strongly correlated one does it even have a metastable minimum, right? For all the others, the electronic energy is just purely concave, all right? And then this is what I showed you before. You will notice that the green one, praseodymium, which is experimentally ordered in our calculation, and we didn't adjust anything, is not quite ordered. This thing is a little higher than that. So that's the level of errors and uncertainties in the calculation. Okay. You can play the same game with films. Since we're running late, I probably won't do that, except to say that interestingly, you can understand these results on the film thickness dependence for solid state professionals a rather peculiar way. This is bulk and two films. What you see is that the quadratic terms around the minimum are almost the same for all the cases, even though the metal-insulator transitions are quite different. And the thing which is changing is the nonlinearities, right? You go out in the wings here, and this one, which is a strain film, is much less than that. Right? So that what the quantum confinement and strain is doing to the electronic properties is lowering the stiffness in the sense of drastically decreasing the higher order nonlinearities and not in the sense of changing the linear response. Right? Which again, somehow goes against everything I was taught in graduate school where, you know, you're supposed to look at the linear response and see what happens. Okay. Calcium ruthenate, more or less the same story. The electronic order parameter is now capped at 1 because it's really you have 4 electrons, at most 2 can go in here. There's a lattice distortion, you can do the same thing. And you see the same story, that if you look only at the electronic part, it's minimized at basically 0. The minimum is not exactly 0 because there's no symmetry. If you add the lattice energy, then it just goes to the as large as an electronic disproportionation as it can be. Okay, so you can, again, write a free energy landscape. Here I've just represented by contour lines the value of the free energy, and this is a diagonal cut going from here up to here. So you see, again, a metastable minimum at 0, 0, a stable minimum here, and nothing anywhere else. So again, in this material, the transition is driven essentially by an interplay of electronic and lattice degrees of freedom. Okay. You can do the same thing with films and more or less reproduce what's going on. We find that the energy is minimum nearly at 0 for this one. By the way, the color coding is bad. The blue one here is the green one here. The blue one here is the red one here. And the yellow one here is the red one there. I'm sorry about that.
We're writing my thermostat.
Yes. But you can see you get essentially the same trends. Basically, very strongly insulating for these two, intermediate for this one, and always metallic for that one. Right? So I think this gives us a reasonable handle on what's going on. With one exception, we do not have a good theory of the temperature dependence. All right. And again, that would take me probably too far afield to go over it in detail. But let me say just that within the theories we know how to do, an electronic disproportionation drives a force on the lattice. Everything we know about the electronic disproportionation says that it's essentially negligibly temperature dependent around here, but you can see that the lattice continues to evolve. So there's something funny going on that we haven't understood in the temperature dependence. And there is similarly in the other material I showed you. Again, if we just run our machinery really as a function of temperature, we predict transition temperatures which are a factor of 2 to 3 higher than they really are. I think we're missing some source of entropy for the high energy phase. Okay. All right. Okay, so that's what I told you so far. And I think I find this very appealing because really there was this long and to my mind, I guess, essentially pointless argument about from the many-body electron school of thought and the density functional lattice degrees of freedom school of thought about which one was in charge of the transition. And now we have a reasonably well-defined mechanism for answering that question in each compound. And in the two we looked at in most detail, the answer is both. Okay. And I should say just that to make this work, really what you require is 3 things. A theoretical method, we use density functional plus dynamical mean field theory, but it's not essential, that delivers an equation of state, and a linear coupling between the electronic order parameter and the lattice degree of freedom. Okay, yeah.
One of them is dominant.
Yeah.
A 2-dimensional plot.
Mm.
That will be in one of the axes, is that right?
Yeah, exactly. And even if it was close to being dominated, there would be other minima here and here.
Basically, all is the equation of state.
Yeah. We put the atom someplace, we calculate the equation of state, so as a function of atomic positions.
Is there a way to directly relate it to what the or
Well, no, because it's a first order transition. So the direct things you can do, you can see that the paramagnetic minimum is locally stable, but you knew that already because it was a first order transition. You know, and indirectly, these experiments on strained films are telling you something. But exactly what, I think, requires an analysis sort of like this to really know. Yeah.
So I guess it's some sort of mixed electron and crystal structure transition, but how do you understand qualitatively what happens with the electrons such that the resistance jumps?
Yes. What happens in this case, in fact, this is in the metallic state. Basically, you have 3 partially occupied orbitals. And it's a minor miracle that that's the case. This is a planar structure. This is not protected by symmetry, but they're pretty nearly equal. So you just have a metallic state. In this case, basically, when you flatten the octahedron, you lower slightly the energy of this orbital. The combination of that and electron-electron interactions makes it be doubly occupied, so it's just a filled shell. These 2 guys combine to make a spin 1, which is a Metal-Insulator. So that's what happens in this case. Just as a sidebar, in fact, there's an interesting complication on top of that where our numerical methods fail. Spin-orbit coupling is not negligible in this compound. You made 2 orbitals to make a spin 1. They also have an L equals 1. And in fact, the ground state is J equals 0. And there's interesting phenomena associated with getting a magnetic state out of a thing where the atomic configuration is J equals 0. But, okay. Oops, I'm going the wrong way. Okay, so now let's ask about dynamics. If I start with the analog of what Ian Fisher did, right? I could take some kind of Landau theory order parameter, Landau theory of an order parameter. I could say I have several order parameters with different coefficients, and I can impose a dynamics. Just for the sake of doing something, let me impose what's called model A dynamics, which is just relaxation. So we have an overdamped order parameter. So it has an equation of motion which says that with some relaxation time, the system wants to relax to the minimum of the free energy. And if you're going to write an equation of motion, then you also need a noise term whose magnitude is controlled by the fluctuation dissipation theorem. So this gives you a stochastic, nonlinear differential equation for your order parameter, and you can use this to discuss dynamics. Okay. Now, in fact, everything we know, and this is a sidebar, says that the basic electronic state relaxes rapidly to a pseudo-equilibrium description corresponding to some electronic temperature. And then there may be exchange of energy with the lattice and so on, which lets that temperature relax. So what I'm going to say is that our dynamics at all times is going to be given by something of this form with a noise like this, and there may be a time-dependent temperature, right? That's, again, the statement that in this model that electrons relax rapidly to a pseudo-equilibrium defined by some temperature, and then over a slower time scale, change their temperature by exchanging energy with some reservoir. Okay, so this gives you an equation that can be solved. All right, so here, what we did was we took, two order parameters. As it were, going back to my superconducting example, a charge density wave one and a superconducting one. Each one has its own Landau theory. There's some cross-coupling. If we make a positive coefficient, they compete. So then you have a free energy landscape, which looks like what I sketched here, right? So this free energy landscape has one minimum, which is superconducting only, one minimum, which is charge density wave only, and a maximum at 0 in equilibrium. And if the system really wants to be charge density wave, then this minimum is deeper. Okay, now what I want to argue is that the ultrafast experiments, which dump some energy into the system, they basically first rapidly heat the system up to a high temperature because you put a bunch of energy in. What that means is you take this free energy landscape and you roll it up into a single minimum at 0. That's what this thing here is supposed to do. Then as time goes on, this thing unfolds into the 0 temperature energy landscape, which is this. And we want to ask, in that time-dependent energy landscape, how does the order parameters move, right? And the very simple argument I want to give you is that if one of the order parameters has a much faster dynamics than the other, for example, because it's not dragging the lattice around with it, then it's very possible for the system to roll down into the wrong minimum just because that minimum has faster dynamics. All right, so you can construct a theory and do this. For theorists who care about this, if you assume that these things have a small Ginzburg parameter, then you get control on the dynamics at the same level. And this is very similar to the standard Kibble-Zurich picture, just with two order parameters and different time-dependent temperatures. Okay, so here's what we did. And again, this is unfortunately spectacularly bad notation of G1s. Well, by the way, I mean G1. I mean, for solving the whole model. The notation is something that is, anyway, the statement is that positive quadratic coefficient means you're in the ordered phase. We define this free energy with a minus here. So positive means you're in the ordered phase. So the idea is that here you're in the ordered phase. The green one says that order parameter 2 is more favored. You hit it with a pump that raises the local temperature, therefore changes the quadratic coefficient to some other value. Now you're in the disordered phase, but the green one, which was more favored, is again closer to 0 than the blue one, which is less favored. All right. Then after a time, the system relaxes. We chose a linear relaxation, but you could put an exponential decay back to equilibrium. It doesn't really matter. All right. So you get a time dependence of these order parameters. At some time, the order parameter first for the more favored one and then for the less favored one crosses 0, and fluctuations of that kind of order start to grow. Right. And the magic of this theory is that because there's a cross-coupling term, it's very possible that, and if there's a sufficiently different time scale, the more favored order parameter grows slowly. You can just see a little bit of green here. So it's not very big by the time the less favored one crosses 0. The less favored one grows more rapidly. And as it grows, it exerts a repulsive force on the more favored one so that you wind up falling down into the wrong minimum just kinetically. All right. You can do this in a slight variant. You can say the order parameters cooperate instead of compete. Then if you have a system which is mostly charge density wave, but slightly superconducting, the the favored minimum is slightly off zero, but you can get the same story that for weak pulses, you just go a little bit away from your minimum and go back. For very strong pulse, you go all the way to the origin, then you relax to the wrong minimum. For intermediate pulse, you can kind of skim around the edge here, right? So this scenario, I think, is what's going on in the superconducting experiments that I showed you. All right. Now I'd like to turn in the last few minutes, and I'm sorry to be running over, to the non-equilibrium experiments that I described to you before. All right, now here, what we, in this case meaning Dennis, did was solve the many-body Schrodinger equation plus the lattice. So we wrote down a theory which has some interactions. We solved it in this so-called dynamical mean field approximation. For aficionados, we simplified the electron kinetic energy a bit and used the so-called NCA solver, right? And that gives us a time dependence of an electron population imbalance, which I'm calling phi here. We also said that you had a harmonic dynamics of the lattice and a coupling which is basically known. So we have two coupled equations of motion, an electronic one and a lattice one, right? And so again, you can solve if you are Dennis. Okay, and what you see here, we have three, oh, and I should say we put in the electromagnetic field that excites electrons and initiates this process. We put that in explicitly. We know how to write the term, which in the presence of an electric field excites electrons from the filled to the empty band. So we say we have an electric field, which is of this frequency and this strength for that long, and you can just put that into the solution. Okay, so you have a relatively weak electric field, you make a relatively small population imbalance, and what you see is oscillations which just stay straight. You have a stronger pulse, you see larger oscillations, and they decay. All right, notice this is 10, 20, 30 femtoseconds. All the experiments were picosecond.
I don't know much about, I guess it's a personal situation, but I don't know anything about all these abbreviations.
Yeah.
How good they are to calculate the efficient times?
Right. Everything we know says that within a factors of 2 or 3, they're reasonably good at getting you to a sort of pseudo-equilibrium state. So if I make my electromagnetic pulse, I populate the upper band in some way, right? Within ballpark of 5 femtoseconds, the electrons will relax to a pseudo-equilibrium state described by some temperature, but still with this population imbalance. And within factors of sort of 2, they're reasonably good at that, right? The case where on the level of model systems, the statement that the recombination across the gap is much longer is also reproduced, but we don't really have good benchmarks to know exactly how good it is. So I think it's all the methods we have say generically recombination across the gap is much, much longer, but how much longer, I'm not sure we have as good a handle on.
But given the equation, suppose you have a single band conductor.
Yeah.
And electronegative interaction described this term. And,
yeah.
Yeah.
Oh yeah. This relaxation to pseudo equilibrium. I mean, yeah, exactly. No, it goes to that. It gives you a time scale which for the metallic electron band thing is not incredibly different from the Fermi Golden Rule time scale. That so on that crude level it makes sense. But for more refined details, I think that it gives you a plausible picture, but I don't think it's been compared in detail. Okay. All right. Anyway, but still you see that there's a low fluence, no change, no long time significant change, high fluence, some change, and calculation is stuck at brutally short time scales. All right. So now, this is just to repeat, what you can do is average over a time window of, let's say, 5 or 10 femtoseconds here. That gives you this dotted line, all right? And that dotted line has a slope, all right? So I can compare the slope to the strength of my initial pulse parameterized by how many electrons got transferred, right? And what you see is that there's a clear break. It's different if you use the bulk material or a thin film for the reasons that I showed you before. It depends on the substrate. But there's clearly a region where the slope is within resolution 0, and then above a certain fluence, it breaks away in ways that are a bit different depending on the system. Okay. Oops. All right. So here what I've done is put these calculations on top of my free energy landscape, right? And what you see is that the initial pulse, if it's weak, just causes the system to bounce around this minimum, right? That's what we expected from our previous calculation. If it's stronger, it shifts you in the electronic coordinate, but not in the lattice coordinate, out to somewhere here. And if it takes you far enough out, then you can start to fall down this way and eventually wind up in this minimum. All right. So I think that this is the picture that explains what's going on. All right. And it says that in particular, the electronic relaxation in particular across the band gap is slow. So rather unusually, the electronic dynamics follows the lattice in this class of problems. All right. Okay. So this is basically what I told you before. And I think we see clearly that that free energy analysis is a useful way to look at the physics of these materials, that many of the interesting transitions have first order landscapes with electronic and lattice degrees of freedom mixed, that static, that is to say strain, and dynamic carrier excitation can be used to steer the order parameter in the landscape. All right. And there's an important open question, which was already asked by several people, which is if the system falls down into the metastable state, how long does it live there? What is really the physics of eventually equilibrating by tunneling out of the metastable minimum back to the true equilibrium minimum, right? And this, I think, is an important open question, which we at least haven't addressed. So I think this is probably as good a place as any to stop in the
Yeah, and I guess my question is connecting back to the nematicity in the iron-based super. My question is connecting back to the nematicity in the iron-based superconductors. Do you have a free energy analysis there? Like, should we be thinking that, because at some point you made a statement that in the equilibrium cases, you always have the two things together. They never show up independently. Would that be true for the iron-based superconductors too? And if so, how do you connect that with the experiments?
No. And I mean, this is, and I should say, this is all really Ian Fisher's work, right? I had nothing to do with this. Right. But the free energy analysis is what you see here, in essence. I mean, this is the way I would write their free energy analysis. All right. And their statement is that in this particular case, it is electronically driven in the sense that this guy will change sign all by itself, even if the lattice doesn't do anything. So all the cross coupling is doing is pushing the temperature up a little bit, right? And this was an important result because there was years of controversy about whether there can be an electronically driven C4 to C2 symmetry breaking, right? And then Leonid had raised the question of what happens here. And to my knowledge, nobody has extended the free energy analysis into the ordered state to make sharp statements here. But basically, you would add quartic terms here, particularly in the electronic interaction. And then there's a fairly obvious set of things you could do.
Thanks, Andy. So you you mentioned there were still things to understand about how temperature drives things.
Yes.
I lost track of whether it was in the same system where you noticed that the variations in the nonlinear response, but if you have an anharmonic phonon system and you
Right.
change the temperature, you start to get
Yeah.
lattice expansion. Are those things connected or?
Yeah. Presumably. We don't have the problem is I think you're doing a bookkeeping of relatively small amounts of entropy. But my personal opinion is that it is anharmonic terms in the phonon, which were not included in our analysis yet, that are eventually going to explain this.
So about the dynamic part, I'm trying to understand the physical picture a bit, if you could explain. So on the one hand, the electrons thermalize quickly to some effective temperature. So that via electron scattering, right? And yet they recombine slowly, which is via electron scattering. Well, how do we square this out?
No, yeah, it's simple. If you have a big gap, all right, then there's a strong kinematic barrier, because if you recombine two electrons, you liberate a lot of energy and it has to go somewhere, right? And because the gap is very big compared to a phonon frequency, you need some kind of multi-phonon process to do it, or if you want it, or multi-magnon if you have that. So there's a kinetic barrier to relaxing across the gap just because you have to find somewhere to put the energy that's released. That's why it's slow.
Because there's not enough other electronic states at high energy.
Maybe there's a process.
Yeah, well, but they don't help you basically, because if you liberate that much energy, right, then typically the Auger or inverse Auger process, what it does is simply kicks another electron up. Yeah, so it doesn't really change your imbalance, and then that relaxes back down.
Thank you.
You decrease the number of electrons, but you don't take energy out of the system. That's your point. Okay.
Right. And just one remark. So you'll notice the way this works basically, and we're still trying to, it's a clear result of the calculation, and we're trying to decide how much we believe it. Look, you see what happens is basically we've changed the electrons. That makes a force on the lattice. The lattice thing goes down. This, in my belief, basically, I mean, it has strange trajectories in here, but basically, it's only when you get down to a place of relatively small lattice distortion, meaning relatively small electronic gap, that the electronic distribution can relax. So it's like in this calculation, you decrease the order parameter a little bit each time you oscillate the lattice far enough down to reduce the gap to be small enough that you get some noticeable relaxation. That's what's going on in this calculation as far as we can tell.
Okay. Yeah, sure.
So if I understood things right, still in this equilibrium picture of these energy landscapes, when you couple these two order parameters, essentially one of them, so to speak, dresses the effective TC that you get. And it seems universally get that this TC goes higher, whereas I would expect that when I couple to something else that could fluctuate, it should promote entropic forces and should drag this TC down. Is that just a matter of the sign of the coupling or something else?
No, it's actually a question of what your baseline is. Basically, roughly speaking, just think of it like mode coupling, right? The cross coupling takes two modes and then it splits them. So the lower one goes down and the upper one goes up. So that's why it always increases the transition temperature by reducing one of the two things. There is a question about fluctuations, right? Which you could put in here. This is all just mean field theory. But basically, the way you should think about this is you have a baseline system which has fluctuations of both order parameters, and then we're adding we're asking how does that get distorted, right? So the fluctuations that you're talking about of two things have been built in more or less as a baseline, right? But there is an analysis which I think nobody has done, where you could just take a theory like this and say, all right, now you have two coupled order parameters. What's the Gaussian fluctuation corrections of both to what happens?
Okay, I think that maybe it's a good time to thanks Andy again. Thank you.
Thank you.